Hi, this is Dr. Goldstein, and we are going to be talking today about how to solve inequalities. So in order to motivate what I'm going to be talking about, I want to start back with solving equations. Remember, if you have an equation that looks like this, 2x squared minus 7x equals negative 3, one thing that we like to do is you add 3 to both sides, and you change this into the equation 2x squared minus 7x plus 3 equals 0. And then you factor this, and this factors as 2x minus 1 times x minus 3. And then you know that this expression is equal to 0 either when 2x minus 1 is equal to 0 or x minus 3 is equal to 0. So when x is equal to 1/2 or x is equal to 3. So similarly, if you are trying to solve an inequality, that is similar, so for example, 2x squared minus 7x is less than or equal to negative 3, maybe we want to start by changing that into the inequality 2x squared minus 7x plus 3 is less than or equal to 0. It was useful for equalities, maybe it'll be useful for inequalities. The nice thing here is that then this becomes a question of where is this expression less than or equal to 0. So where is 2x squared minus 7x plus 3 non-positive? So either equal to 0 or less than 0. And so the question of solving an inequality becomes this question of where does an expression change sign? So what I mean by that is where does it go from positive to negative or from negative to positive? And if I know where it changes signs, I can figure out where it's positive and where it's negative via the method that I will be showing you in the later examples. So stay tuned. Okay, we need a couple of properties. So the first property is that a polynomial can only change sign at values where it is equal to 0. So here is an example to explain why that's true. If I look at the polynomial x squared minus 1, I can factor it as x plus 1 times x minus 1. So what this property tells me is that this can change sign. This can change sign when x is equal to negative 1 or x is equal to 1, because that is where x squared minus 1 is equal to 0. This is because x squared minus 1 is equal to 0 there. And if we look at the graph of x squared minus 1, which is what I have at the right, we can see, okay, here's the minus 1 and the plus 1. That's where it is equal to 0. So this is minus 1, and here is 1. And we can see that indeed the expression does go from positive to negative at minus 1, and then switches back from negative to positive at 1. So this expression can change sign, and it does change sign when x is equal to 1 or minus 1, and that's because that is where it is 0. So our next property is that a quotient of polynomials can change sign only at values where its numerator or denominator is equal to 0. So here's another example for you. If I look at this quotient x plus 1 over x minus 1, we see that the numerator is equal to 0, so the top is equal to 0 when x plus 1 is equal to 0, and so when x is equal to minus 1. And if we look at the picture, yep, our graph goes from positive to negative. And if we look at where the bottom is equal to 0, this happens when x minus 1 is equal to 0, so when x is equal to 1, and that's what we have over here on our graph. So this vertical asymptote is at x equals 1, and we see that the graph, which was negative to the left of that, is positive to the right of that. So at x equals 1, the graph goes from negative to positive. And to summarize the idea behind both of these properties, the graph either has to jump or go through 0 in order to change sign. So we can see in this picture at x equals minus 1, where the graph is equal to 0, we have a change of sign. And then at x equals 1, where the graph has a jump, our graph can change sign as well. So that is the idea behind these two properties. Now, let's see this applied to a problem. So here's our inequality from before, and we want to solve 2x squared minus 7x is less than or equal to negative 3. So the first thing that I'm going to do with this is I'm going to move everything over to the left-hand side. So I have 2x squared minus 7x plus 3 is less than or equal to 0. So again, now this becomes a question of where is this positive, where is it negative, and we happen to want the negative part. And now we factor to 2x minus 1 times x minus 3. And we say, okay, then this can change sign. This is a polynomial, so it can change sign when it's equal to 0. So it's when x is 1/2 and when x is 3. All right, so here is the kind of complicated part. In order to figure out where this expression is positive and negative, I know it can change sign at x equals 1/2 because that's where it's equal to 0, and it can change sign at x equals 3. The idea here now is that I can pick a single point on each interval to plug in. And once I figure out whether my expression is positive or negative at that single point, I know that it's either positive or negative on that entire interval because I know it can't change. So what I am going to do is on this interval to the left of 1/2, I'm going to pick a nice easy number. I'm going to use x equals 0. Between 1/2 and 3, again, I'm just going to make this easy on myself. I could pick whatever I want, but I'm going to work with x equals 1 just because it's easy. And then to the right of 3, I'm going to use x equals 5. You could use 4, you could use 7. It makes no difference. So now if I plug those in, So we're looking at the easiest one to work with here is going to be this factored inequality. This is what my problem has become. So if I plug in x equals 0, I get 2 times 0 minus 1 times 0 minus 3. This is minus 1 times minus 3, which is 3. And so on this entire interval, I know that this expression is positive. If I plug in x equals 1, so this is 2 times 1 minus 1, 1 minus 3. So this is 1 times negative 2. I get a negative number. So again, I know on this entire interval, my expression is negative. Now, if I plug in the last x equals 5, I have 2 times 5 minus 1, 5 minus 3. So this is 9 times 2 is 18. So again, on this entire interval that goes off to infinity, I know this expression is positive, and I look back at the expression that we're working with, and we want it to be less than or equal to 0. So we are looking for this interval right here where our expression is negative, and we want to include the endpoints because we want less than or equal to 0. So our solution is that x can be anywhere from 1/2 to 3, including the endpoint. So that is our solution in interval notation. So again, summarizing this whole process, we've begun with an inequality that we transform into a question of being greater than or less than 0. And then we can use this number line to test only a couple of points. We plug those in, and we determine everywhere where this expression is positive and negative, and then we pick the part that we want. So this is a really complicated process. It's going to be super useful for all sorts of things. I am going to show you one more example. It's a little bit on the complicated side, so if you're already feeling a little bit cross-eyed, you might want to stop and come back at this point and look at the last example later. But I am going to show you one more example. So let's deal with a rational expression. So we want to solve 1 over x plus 1 is greater than or equal to 4. As before, I want to move everything over to one side. So I have 1 over x plus 1 minus 4 is greater than or equal to 0. And then I need to simplify this. And in order to do that, I need to put everything over a common denominator. And then when I simplify that, on the top I have 1 minus 4x minus 4 over x plus 1. And so I end up with minus 4x minus 3 over x plus 1 is greater than or equal to 0. And so remember what we said back a couple slides ago is that when we have a quotient of polynomials, it can change sign. When either the top or the bottom is equal to 0. So I need to worry about when minus 4x minus 3 is equal to 0, or when x plus 1 is equal to 0. So in the first case, I get that minus 4x minus 3 is equal to 0 when x is minus 3/4, and x plus 1 is equal to 0 when x is equal to minus 1. So focusing on what we've changed our inequality into, I want to figure out this question. And to do that, I use a number line. And the numbers that I put on my number line are the places where my expression can change sign. So I have negative 1, and I have negative 3/4. Now, on the last slide, I put a 0 above both of the numbers because our expression was 0 there. Here, this expression is only 0 when x is equal to negative 3/4, because when x is equal to -1, the bottom is 0, and so this expression actually is undefined. It does not exist when x is equal to -1, and I want to keep track of that. Okay, so the next step in our method is to pick a point on each of these intervals to plug in. So I'm going to plug in x equals -2. I'm going to plug in, if you think of -3/4 as negative 0.75, I can plug in negative 0.8. And over here, I'm going to make my life easier. I'm going to plug in x equals 0. So I am plugging everything into -4x minus 3 divided by x plus 1. So I'm going to create a table for doing this. So this is -4x minus 3 over x plus 1. And I am plugging in, whoops, this wants to go down here. So I am plugging in x equals -2, I am plugging in negative 0.8, and I am plugging in 0, and I'm plugging it into -4x minus 3 over x plus 1. This is best done on a calculator, I think. When I plug in -2, I end up with -5. When I plug in -0.8, I end up with 1, and when I plug in 0, I end up with -3. And so my expression is negative to the left of -1, positive between -1 and -3/4, and negative again to the right of -3/4. So working from what our inequality became, we want greater than or equal to 0. So what we want is this interval right here, but we have to be careful of the fact that our expression does not exist when x is equal to 1. -1, sorry. So because of that, we can have x anywhere greater than -1 and less than or equal to -3/4. Equal to 0 is okay. Does not exist is not okay. And so our solution in interval notation is the interval from -1 to -3/4. And that is our solution to this problem. So again, it's complicated. Why bother with this, you might ask? So I'm going to show you one more thing. I'm going to show you a wrong solution. So we're going to look at the exact same problem, and I'm going to do it the wrong way. So one thing that might be tempting when you look at this, so again, all of this that follows is wrong. When I look at 1 over x plus 1 is greater than or equal to 4, you might say, oh, we'll just multiply both sides by x plus 1. That'll make it so much easier. That'll make it so much easier. And then it cancels out on the left-hand side. Great. And then we end up with 1 is greater than or equal to 4x plus 4. And so subtracting 4 from both sides, we have -3 is greater than or equal to 4x. Dividing by 4, we have x is less than or equal to -3/4. And we say, oh, that was so much easier. There we go. Again, this is wrong, and you can see that. You can check, for example, x equals -2. And if I plug that into the original problem, I have 1 over x plus 1. If I plug in -2, I get 1 over -1, which is -1, which is not greater than or equal to 4. So we can ask ourselves, why doesn't this work? What did we do? Remember that when you multiply an inequality, so when you have an inequality, you have to flip the inequality sign if you multiply by a negative number. If you multiply by a negative number in an inequality, you have to flip the inequality sign. And right here, in this step, we're multiplying by x plus 1. And remember, this is a real expression. This stands for a real number. X could be anything, so x plus 1 may be positive, may be negative. So we don't know whether to flip the inequality or not. So this is why we get this false solution, because we've done this illegal step of multiplying by something that might be positive or might be negative. You can't do that when you're working with an inequality, and this is precisely what makes working with inequalities so hard, and that's precisely why we want to bother with this complicated method using this number line. The number line method, again, it's very, very complicated. Go back and watch those parts of the video a couple of times to get the hang of it before you give up on it entirely. But yeah, happy solving.